So today our focus will be on the air interface, the way UE and E node B, the base station, communicate with each other. And as we have mentioned in the past, LTE long-term evolution is a 4G technology, and over the air, instead of using CDMA, which we do in 3G, now we are using OFDMA based techniques. And first part of the session, we will discuss the fundamentals of OFDMA. And once we are done with that, we will move on to the downlink multiple access technique that we use in LTE. So that would be OFDMA. And finally, we will take a look at SC-FDMA that is used in the uplink, UE to the E node B. SC-FDMA is a variation of OFDMA, and you can think of SC-FDMA as OFDMA with a twist. And why we do that, we'll see. Okay. Okay, and just like I have said in the past, my background, I have taught courses, worked on designing algorithms related to 1x, 1x video, UMTS, YMX, LT, etc. Okay, before we get going, please tell me about your work, the type of work that you are doing. Okay. I will give you a few more seconds. Looks like some folks are still thinking. Okay. Thank you. So this is what you guys are telling me. So about 50% system test integration, 20% customer support, hardware software about 16. Okay. So basically. Okay, or you different types of things. Okay, thank you. Just one more question, and then we will start covering the material. Okay. Okay, how much you want the session to be detailed? Little detail or lots and lots of details? I'll give you a few more seconds. Okay, very good. So this is what you are telling me. So, okay, so here is the situation. Let's say about 50-50. 50% want less detail, 50% want more. Okay, so what I will try to do, okay, on my part. I will try to keep it sort of at the medium degree of details, and if you want more details, just ask questions, okay? And when I'm answering those detailed questions, and if you are just looking for high-level view, please have patience, okay, as we work through the details, okay? We really appreciate your patience, because as you can imagine, right, it's difficult to address different levels of detail requirements, but to help everyone, we'll keep it at a medium degree of details. And if you want more details, of course, please ask questions. My sole purpose today, okay, for the next several hours, I exist for you. Anytime you have questions, please send those questions my way. That is the best way to get maximum mileage out of this session, okay? and we appreciate you. And you have been doing a very good job of asking questions. And in case I do not have the answer, I will try to do some study and get back to you. Okay. And as Dan mentioned, you should have access to the PDF file, and that PDF file has all the acronyms listed. Okay, so feel free to make some notes on the hard copy of that PDF or whatever you want to do. Okay. Okay, and this is what we have for the next several hours. We would like to have the basics of OFDM covered. Okay. And OFDM orthogonal frequency division multiplexing. Quite efficient technique that will help us achieve very good spectral efficiency. OFDM has some challenges, and we will take care of those challenges by using the solutions such as cyclic prefix and so-called adequate subcarrier spacing. OFDM systems typically suffer from so-called high peak-to-average power ratio. On average, the power being transmitted may not be that much, but sometimes suddenly we have a need to transmit more power. So the peak power could be high compared to the average power. So that is the so-called high peak-to-average power ratio problem. And different techniques exist to solve that kind of problem, and we will see that in LTE we use a variation of OFDMA called SC-FDMA to solve that kind of problem in the uplink. We would like to give you an idea about the transmitter and the receiver in an LTE system. Okay. And finally, we will see what is the difference between OFDMA and SC-FDMA. OFDMA downlink, SC-FDMA used in the uplink. So that's what we plan to cover. Now, to the basics of OFDM, we would like to have a strong foundation because OFDM is used in both uplink and downlink, right? OFDM is the basic technique, and a special case of OFDM would be OFDMA, a special case of OFDM would be SC-FDMA. So OFDM is the foundation. So let's see what this OFDM is all about. Tomorrow morning, when you take shower, think of OFDM. What happens when you take shower? Water is coming, okay, from a big pipe, and the shower head distributes that water into many tiny streams of water. Each stream carries very little water, but what is the end result? Nice user experience. If the water is warm, if it is cold, all bets are off. That's how OFDM works. Large amount of data is sent on many radio channels, hundreds and thousands of radio channels. Each radio channel carries a little bit of data. In this case, only 100 kilobits per second. But if you have 100 kilobits per second in one channel and you use, let's say, 100 such channels in parallel, okay, in that case you can imagine that you will get very high data. In this case, let's say 10 megabits per second. And in LTE, do you remember what is the highest data rate in the downlink and highest in the uplink? You can give me the answer through questions and answers box. Highest data rate in LTE. Okay, 300 in the downlink. Very good. 300 megabits per second in the downlink. How about the uplink? Do you remember? Okay, I have not yet got the correct answer. Oh, 75. Very good. Good. Thank you. So, 300 in the downlink and 75 megabits per second in the uplink. So this is what we can support in LTE. Okay, and if you are curious, there are several categories of user equipment, and category 5 UE will be able to support this kind of data rates. Category 5. Okay. And some folks mention 100 megabits per second. So let me just quickly revisit. The target data is, when we started out LTE work, we said, okay, what is our target? We wanted to get more than 100 in the downlink and 50 in the uplink. These were our targets. But when we actually designed the standard, right, we said, okay, we can do way beyond that. Okay, we can really do 300 in the downlink and 75 in the uplink. Thank you very much for giving the answer. Okay. Okay. Good. So, in summary, we have OFDM system in which parallel transmission on multiple radio channels gives us very high data. That is the main idea. Now we mentioned transmission on multiple channels. So in a traditional multi-carrier system, we have some bandwidth that we divide into many carriers. So let's say carrier 1, 2, etc. And one channel carries, let's say, 1 megabits per second. So here we have 6 total subcarriers, 6 total carriers, and that will give us a total of 6 megabits per second data rate. Okay. And we have some comments. Okay. Now LTE, right? So work in progress, and that's why in some other class you might have seen 80 megabits per second. Okay, but now 75 is what is in the standard. Okay, so thanks for pointing that out. Okay, so earlier we might have mentioned 80, but now this is the latest and the greatest. Okay, because this is really in the standard right now. Okay, so 75 is the most accurate number. Okay, because that is the defined now. 75 in the uplink, 300 in the downlink. It's slightly more than 300, but close to 300. Okay, so let's say we have a traditional multi-carrier system. In that case, if you observe between 2 adjacent carriers, we have some sort of guard band. Who will tell me the benefit of having a guard band in a traditional multi-carrier system? Why do we have guard between 2 carriers? Any benefit? Interference, correct. Okay, very good. Thank you very much. So the main idea behind this guard is we want to minimize interference between adjacent channels. That is the idea. Okay. Now, if you think of OFDM, then we put all those channels very close to one another. So now there is significant overlap, as you can see here. Right? So one carrier and another carrier, very close, significant overlap. So in general, when you have significant overlap, you would think that, oh, there is a lot of interference. In fact, in OFDM, zero interference, absolutely no interference between any 2 carriers, even when there is significant overlap. Now, what is the magic that we are doing? Why do we have zero interference even in the presence of significant overlap? No guard. Remember, in OFDM, there is absolutely no guard band between 2 adjacent carriers. And the magic is this orthogonality. 2 carriers are orthogonal to each other. So when we have some spectrum, let's say going from here to here, okay, then we divide the spectrum into many carriers. Okay. And we have significant overlap. So let's say how many we could squeeze in. 1, 2, 3, 4, 5, 6, etc. 12. Okay. So I could squeeze in 12 carriers. and if each carrier carries 1 megabits per second, my data rate now is 12 megabits per second. So let's compare that with our traditional multi-carrier system, 6. So instead of 6, we are doing now 12 megabits per second, right? So we are able to squeeze in more carriers, and each carrier will carry some data. So parallel transmission on more carriers will give us even higher data rate. In this simple example, I increase my data rate by a factor of 2, from 6 megabits per second to 12. So that is the idea, that since we do not need to worry about overlap, since there is absolutely no guard band between two adjacent carriers, we can put many carriers, and then we will have very high data rate. The key to the OFDM systems is orthogonality. Now, just like the volt scores in our regular 1x systems, just like the volt scores are orthogonal to one another, just like OVSF codes in UMTS are orthogonal to one another, just like that, the carriers in OFDM systems are orthogonal to one another. And as you know, whenever there is orthogonality, there is no interference. And now we have some questions and actually the answers. Okay, good. So some of you are answering the earlier question about the guard. It's all about interference. Okay. Now there is a question here. What about Shannon capacity? Well, we are, as you know, we can keep coming up with better and better modulation schemes, the higher order modulation. We can keep using advanced antenna techniques, right? So that will give us very high performance. So few years ago, I got a news story that Lucent folks are shattering the Shannon capacity limit by using the techniques such as this MIMO. You have a system called BLAST, Bell Labs layered architecture in space and time. So basically, now we are going to use better and better techniques, signal processing techniques, and that will help us achieve very high capacity. Okay. Now, how do we achieve orthogonality? Okay, we will discuss that. Okay, how to make sure that we have orthogonal carriers. So we'll discuss that. Okay, good question. In fact, the very next slide, okay, this will tell us how to construct orthogonal carriers. Okay. Now let's start using correct terminology. Each carrier, each radio channel here is formally called subcarrier. Okay, subcarrier. And let's say I have a spectrum. I am a service operator and I got some spectrum from FCC, and I have divided that into many subcarriers, F1, F2, F3, etc. And now let's see how to construct the first subcarrier. Okay. So this is my first subcarrier, F1. So I will pick some time period which is modulation symbol period. Okay, so during the modulation symbol period, we send out just one modulation symbol, that's it. So during one modulation symbol period, only single modulation symbol is going out on that specific subcarrier. Now, can you tell me what is this modulation symbol? What does it represent? Modulation symbol, what does it represent in simple terms? Modulation symbol. Who will tell me modulation symbol? Okay, data, each user, okay, data, correct. So one or more bits, very good, very good. So thank you for answering questions. So a modulation symbol, let's say this is one modulation symbol. So it represents data bits. So a given symbol may represent one or more bits. So if it is BPSK modulation, binary phase shift keying, then this symbol represents just one information bit. And if you want to be more accurate, it is one code symbol, turbo code symbol, etc. If you are using QPSK modulation, 2 bits are represented by a single modulation symbol. And by the way, the highest order modulation supported in LTE is 64 QAM. Then 6 bits are represented by a single modulation symbol. So if this is a 64 QAM modulation symbol, it may represent this set of 6 bits. So when we send a single sine wave, this kind of waveform, this kind of signal to the user, and we tell the user that, by the way, this is a 64 QAM signal, then the user knows that, oh, this signal corresponds to a set of 6 bits, 0, 0, 1, 1, 0, 0. Okay. So the meaning of each type of waveform is predefined in the standard. So if we have another kind of waveform, something like that, okay, this may represent another modulation symbol, and for example, it may correspond to another pattern, let's say 1, 1, 1, 1, 0, 0. Okay. So the standard defines exactly how to interpret the received signal structure. So depending on what kind of waveform we get, we know that that corresponds to a specific set of bits. So in summary, a modulation symbol represents one or more bits, and that time period during which we send one modulation symbol, that is your modulation symbol period. And in LTE, that symbol period is exactly 66 microseconds. So 66.666 keeps on going microseconds. That is the time period in LTE, modulation symbol period. So if you want to calculate what is the frequency of that subcarrier F1, then of course frequency is 1 over time period. So 1 divided by 66 microseconds, you will get 15 kilohertz. So 15 kilohertz is the frequency of the first carrier. Then if you look at the second one, we have 2 cycles. One cycle here, another cycle here. We have 2 full cycles. Okay, so in that case, the frequency of the second subcarrier will be 2 times the first one, which is 30 kilohertz. Then if you look at F3, okay, F3, then we have 3 cycles. 1, 2, and 3. 3 full cycles. So it will be the 3 times the original frequency. Okay, and you will get 15 times 3, 45 kilohertz. So now, if you observe, the difference between adjacent subcarriers is exactly 15 kilohertz. So that is the subcarrier spacing. So between 2 subcarriers, the spacing in LT is always 15 kilohertz, fixed in the standard. So for a regular cell that is supporting several UEs, email, web browsing, those kinds of applications, that kind of a cell will use the subcarrier spacing of 15 kilohertz. So same way between F2 and F3, 30 kilohertz and 45 kilohertz. What is the difference? Again, 15 kilohertz. Now that 15 kilohertz is nothing but 1 over the modulation symbol period. So in summary, in LTE, we are using the modulation symbol period T, 66 microseconds, and it will fix our subcarrier spacing as 1 over that period, which is 15 kilohertz. So basically, subcarrier spacing is 1 over the symbol period. And since in LT we have 66 microseconds as our symbol period, we have always 15 kilohertz as the subcarrier space, always fixed. Okay, so we have
Nishis, you do have some questions in queue.
Yes. Orthogonal frequencies. So okay, so now when we say we have orthogonal subcarriers, then there is no interference among them. So no interference. And okay, so let me, looks like you want more details. So let me give you a mathematical analysis of how you can prove that the subcarriers are orthogonal. And for those folks who just are looking for high-level details, please have patience as we go through this. Orthogonality among subcarriers. So we'll take a simple example. So we have F1. We want to send bit A to one user, and we have bit B going over F2 to another user. Okay. So the base station is sending out a signal that has 2 bits, 1 bit going to one user, another bit going to another user. So bit A is carried over 1 carrier frequency, and bit B for another user is being carried over second subcarrier. Okay. So all users receive this signal, right? The combined signal. Okay. So now let's pretend that you are UE1. What will you do? Okay. In the past, we have told this UE1 that your data will arrive on F1. So this UE has now a reference signal, and it is looking for 1 cycle of sine wave F1. So the reference signal for that UE number 1 has the structure sine that has a single cycle during the modulation symbol period. So this is how we will process the signal. Whatever signal we get, received signal, we will multiply that by our reference signal, and then we will do integration over the time period t, 0 to t, and of course that is 66 microseconds in LT. So let's do simple calculation. So received signal is a sine wave at 1 carrier frequency and sine wave at another carrier frequency. This is the received signal. But now, as UE1, we know that our reference signal is F1. So let's multiply the received signal by F1. Then we will do integration by parts. So we will have sine square at 2 pi F1t, and then we will do another integration, right? Sine at 2 different carrier frequencies. And now let's see. So we have sine and square of the sine wave. Okay, so we have a sine wave F1, another sine wave. Okay, and now we are squaring them, so we are multiplying them. So let's multiply. This is positive, this is positive, this is negative, this is negative. Okay. So now if you want to do sine square, then let's multiply those sine waves. Sine wave here, sine wave here. Plus, plus, you will get plus. Yeah, multiply 2 positive numbers. Right? You will get a positive number. Multiply 2 negative numbers. Again, you will get a positive number. And what is the integration? Integration is nothing but the area under the curve. And this is that area. This area, right? So everything is positive. So you add 2 numbers, you get a big positive number, let's say constant k. So if you have sine square, okay, and if you do integration, you will get some constant k. On the other hand, if you do sine square integration, you will get some constant k, a times k. Now let's see what we get when we do integration, where we multiply two sine waves at different frequencies. Okay, so f1 and then f2 . Okay, so plus and minus, plus minus, plus minus. Okay, so plus and plus, right? Two positive numbers, so we'll get some sort of positive value there. Plus and minus, you will get some sort of negative number. Negative and positive, you multiply, you will get some negative numbers. And finally, negative and negative, two negative numbers, you get some positive. Right? And because of the symmetry, this plus, and now let's do the integration. Area under the curve. Right? Plus minus, right? So they will cancel out with each other. And the answer will be 0. Right? You add plus and minus, you will get 0, minus plus, area under the curve, 0. So when you have two sine waves where the frequencies are integer multiples of a base frequency, f1 and f2. This was f1, this was f2. So when you multiply those and do integration, answer will always be 0. And this is what we have. Answer is 0. So we got a times some constant k. Okay, what is this a now? This a is nothing but what base station was trying to send us on f1. Because we have told the user that your data would be arriving on f1. So in summary, as shown by this mathematical processing, we have orthogonality among the subcarriers, because your reference signal and the received signal, when you multiply and do integration, you will be able to recover your information with every other subcarrier. When you multiply and integrate by your reference signal, it will always give you 0. Okay, so this is how we can show that the carriers are orthogonal and we do not need to worry about interface. Okay, some other questions, we will take care of those now. Okay, and by the way, thank you very much for giving the answer. Can it be non-contiguous? Yes. Okay, so can our subcarriers be non-contiguous? Correct. So I can give, let's say, okay, now for LTE, okay, so let's talk about a user, and we give the user in the downlink two sets of carriers. So let me draw a picture here. So one user, okay. Okay, now I'm giving you answer for the LT, because you asked the question, can the subcase be non-contiguous? So short answer is yes, they can be non-contiguous. But I need to give you a little more details, otherwise my answer will look incorrect. Okay, so if you are a user, then you may get two sets of subcarriers. So let's say here is my frequency spectrum. Then you may get one part of the spectrum perhaps here, and then this is another part of the spectrum. So basically this has 12 subcarriers. Okay, and then this is another set of 12 subcarriers. So it is possible that as far as the allocation is concerned, one user in the downlink may get two different sets, and in that case they are not contiguous. But within this set, we have 12 contiguous sets. Within a set, we have 12 consecutive or contiguous subcarriers. And that set formally is called resource block in LT. So one resource block has 12 consecutive subcarriers. So hopefully that answers your question. And as I have mentioned in the past, asking questions is the best way to get the maximum benefit. Okay. And when we are discussing that, and if it is too detailed for you, please have patience. Okay, we appreciate your patience. Okay. So that's that question. And are you talking about baseband? Yes, baseband. We are yes, correct. Another question is, are we talking about the subcarriers at the baseband? Yes. So far, everything we have talked about is baseband. That is correct. Absolutely correct. Everything at the baseband. Okay. Okay. And then another question that we have is F1 the modulation frequency or the carrier? Okay. So at the baseband, that is the frequency of the first subcarrier. So let me give you a little more info. Okay, so let's say we have F1 here, F2 here, okay, and now this is the baseband picture. So F1 will be at 15 kilohertz frequency, okay, F2 at 30 kilohertz. So if you have the last subcarrier, let's say 1024 number, it would have the frequency of about 15 megahertz. So now we are occupying a spectrum 0 to 15 megahertz, but this is all at the baseband. So after you do frequency up conversion, then we will shift that spectrum all the way to RF. So then we will have the center RF. Let's say we deploy at 700 megahertz. That is one of the carrier frequencies at which LTE will be deployed. Okay, Verizon got a lot of spectrum. AT&T has some spectrum at 700 megahertz. So now we will occupy that spectrum at 700 megahertz. So this would be the center carrier frequency. Center carrier frequency. And of course, then this F1, right, that will be the first one here. And the last at 1024 will be 1024. Okay, so hopefully that answers your question in sufficient detail. So basic, okay, another follow-up question. Subcarrier are orthogonal because they are multiples of one. Correct, at the baseband. Absolutely correct. So they are multiples of the base frequency. Absolutely correct. Very good. So let's go back to our discussion of the basic OFDMA. Okay, so now we know how to construct orthogonal subcarriers. Okay. So if you have a spectrum analyzer, and if you look at how much power you have at various carriers, various subcarriers, this is what you will observe. Okay. So let's say we are a UE that has been allocated F1. Okay. So we look at that F1. Okay. So the x-axis is the frequency, and you can think of this as baseband. Okay. So it will be easy to visualize baseband. Now the resolution in live meeting is not very, very high. So sometimes when I write, it's a little bit difficult. I understand that. Okay, but I will try to be as legible as possible. Okay. So F1, and at that time, this y-axis is the amplitude, and amplitude square would be power. So when we are observing our subcarrier frequency F1, let's say 15 kilohertz, then at that time, whatever power we are getting, that is our signal power. So we have pretty good power. Let's see how much interference we are getting from other subcarriers which are going to some other users. So let's talk about F2. So F2, signal, amplitude and power going down. It will cross the zero amplitude, so zero power, meaning we are not getting any interference from F2. So when we look at our own carrier frequency, F2 gives us zero interference. How about F3? Here is F3 going down, going down, going down, and again that signal will cross the zero amplitude, zero power. So basically, when we are looking at our own subcarrier F1, every other subcarrier will cross zero amplitude. It means we have zero interference coming from every other subcarrier in the system. So we have very high signal power and zero interference ideally. So we have very, very high signal to interference ratio, and we should be able to recover the information that is coming on our F1. So that is the main idea. And of course, the spacing between two subcarriers right here is 1 over the modulation symbol time, 1 over 66 microseconds, 15 kilohertz, rock solid, fixed in the standard. Cannot change it, not 10, not 12, exactly 15 kilohertz. And that is 1 over the symbol time. Okay, absolutely fixed. Okay, so now let's get understanding of some other term. Okay, now I will give you a very simple rule of thumb. Okay, during the modulation symbol period, one subcarrier carries one modulation symbol. Very, very simple rule to remember. So if I have some modulation symbol period which is 66 microseconds, during that time period, one subcarrier will carry one modulation symbol. Okay. So in our example here, we have 1, 2, all 3, 4, 5, and 6. We have 6 subcarriers. Okay. And one subcarrier will carry one modulation symbol. Another subcarrier, second modulation symbol. And similarly, the last subcarrier will carry the 6th modulation symbol. Okay. And we of course know the symbol time is 66 microseconds. Okay. So now basically we are sending data on 6 subcarriers in parallel. One subcarrier, one modulation symbol. And now let's calculate what data rate we are getting. Okay. So we'll keep it very simple and calculate data. So in our example, we have 6 subcarriers, and that should be able to send out 6 modulation symbols, one on each subcarrier. Now the data rate, of course, the number of bits per time period. The time period we know, approximately 66 microseconds. Now how many bits? 6 modulation symbols. Now what modulation symbol? So we have various techniques. What is the highest order modulation scheme in LTE? Highest order modulation scheme? Highest order. And how many bits does it represent? Okay, 64 COM and 6 bits. Perfect, perfect. So let's say these are 64 COM modulation. And each 64 COM modulation symbol represents 6 bits. So 6 bits per modulation symbol. Okay, so we got 36 bits being represented in 66 microseconds. So let me do a simple calculation. 36 divided by 66. I got 0.5 megabits per second. Okay, so if I have 6 subcarriers, my data rate is 0.5 megabits per second. If I have 600, I will get 50 megabits per second. And if I have 1200 subcarriers, double that number, 100 megabits per second. Okay, in LTE, when we have 20 megahertz spectrum, inside that we will have 1200 subcarriers that can carry data. So those are the usable data subcarriers. The subcarriers we can use to send out data modulation symbols. And in that case, we can get 100 megabits per second. Now, the instructor has been claiming 300 megabits per second, and I reached only 100. Oh, so something is still missing. Okay. Now, if you remember from yesterday, I said that OFDMA alone is not sufficient to give us the highest spectral efficiency, the highest data rate. We have the advanced antenna techniques as well, right, that we need to use. And the specific technique that we are currently interested in is MIMO, multiple input, multiple output. So we have 4 antennas. So we are using 4x4 downlink MIMO. So in that case, 4 antennas at the base station and 4 antennas at the UE. 1, 2, 3, and 4. One antenna is sending out 100 megabits per second. Another antenna sending out 100 megabits per second, and so on. So basically, each of the 4 antennas is sending out 100 megabits per second. 100 times 4 antennas, we are able to get 400 megabits per second. But I just need only 300. So it means 400 minus 300, I have about 100 megabits per second worth of data, and that will be my redundancy. So in simple terms, we have 300 megabits per second, and then I will do the coding, meaning add a redundancy, and after I add redundancy, I will get 400 megabits per second. Okay, so 300 megabits per second, think of these as raw data. So now you know how to get, in simple terms, how to get 300 megabits per second, the highest data rate in LTE. Basically, you have to use the entire 20 megahertz spectrum, and on each of those 1200 subcarriers, you will have 64 modulation symbol being transmitted. Not only that, you will use the same 1200 subcarriers from each of the 4 antennas. Okay, so you are reusing the same set of subcarriers from each of the 4 antennas, and that will give us highest data rate. So on yes, we have a question that how can we use the same carrier same set of subcarriers on all antennas? So basically, we'll cover more details later. We have one whole session dedicated to advanced antenna techniques. But basically, this UE will separate them in space. Okay, so we are relying on the environment to influence those signals in a different way. So signal on one antenna is changed by the environment. Signal 2 is changed by the radio environment, but the environment will change those signals in a different fashion. For example, there will not be any phase shift on antenna 1 signal. Maybe antenna 2 signal is experiencing 45-degree phase shift due to the radio environment. So things like that. So we will do the digital signal processing to figure out how the environment is changing the signals, and we will use that knowledge to recover the information coming from different antennas. Okay. But basically we are separating them in space. Okay, that's why this kind of technique is called spatial multiplexing. But of course, I will give you more information in a future session. Okay, the whole session is dedicated to advanced antenna technique. Okay, so hopefully this will suffice at this time. Okay, 20 megahertz. Someone did the calculation that 20 megahertz gives 1333 subcarriers. Okay, so let me address that question. And again, we really appreciate you guys asking questions. Okay, the more the questions, the better. You are not only helping yourself, you are helping your friends. your colleagues. So one participant is saying that, okay, you have 1333, okay, in 20 mega spectrum based on the spacing. The spacing, of course, 15 kilohertz, and spacing is always 1 divided by symbol time. Okay. Now, but we said, okay, we can use only 1200. Okay, the question is why we use only 1200 out of 13. Okay, the short answer is to meet spectral mask requirement. The FCC has given us this spectrum 20 megahertz, so we cannot send our signal outside of that. So what we will do, we will have some portion on the left side, some portion on the right hand side, and those left and right side. Oh, I need to expand that a little here. Let's say expand a little this side. Okay. So that spectrum is nothing but the guard. So the last subcarrier will transmit. These are 1200 active data subcarriers, and these are guard, meaning the last subcarrier will transmit. Let's say this is transmit signal power, then it will go down, go down, go down, go down. And similarly, this will go down in signal strength, go down, go down. And by the time we reach edge of our spectrum, okay, the signal is now very, very weak, and we are able to meet the FCC spectrum mask requirements. No interference to adjacent spectrum, because we are given only 20 mega spectrum. We cannot start causing interference to the folks who are using this part of the spectrum or who may be using left edge of the spectrum, because this is maybe another operator. Okay, we do not own that spectrum. Okay, if we had started sending signal on F1, right, it would be very, very high, and we would not be able to contain the signal. We'll start causing interference to the adjacent system. But very good question. Very good question. Keep those questions coming my way. Excellent questions. Okay. Let's see. Okay. So now we know how to get high data rate. Okay. Orthogonality, zero interference, squeeze in many subcarriers. Each subcarrier carries one modulation symbol. Parallel transmission of modulation symbols on many subcarriers gives us super duper data rate. Okay. Now one term that we should be familiar with, that is so-called OFDM symbol. Now what is this OFDM symbol? Very, very simple. It is the combination of all modulation symbols on all subcarriers. So when you combine all the modulation symbols going on all subcarriers, that is your OFDM symbol. And that is the definition. Okay, let me summarize again. OFDM symbol is nothing but combination of all modulation symbols on all subcarriers. So if you recall in 1X, 1X EVDO and UMTS, in those 3G systems, what goes over the air is chips, right? 1.2288 mega chips per second in 1X NDO, 3.84 mega chips per second. So what goes over the air in CDMA systems is chips. On the other hand, what goes over the air in OFDM systems is OFDM symbols. So the base station will send out OFDM symbols. The UE will be sending out OFDM symbols over the air. Okay, so that's our OFDM symbol. Okay, we have questions. Correct. So if we have 10 megahertz deployment, correct, then we will have 600 data subcarriers. Absolutely correct. So it's just a simple linear relationship. Okay, very good. Right. You guessed it right. Okay, now we said that we divide the spectrum into many subcarriers. Well, we have different types of subcarriers, and what we are showing here is for a generic OFDM system. So it's not necessary that it will apply to our LTE in exactly the same fashion. Okay, but it will be sufficient at this time to get understanding of various types of subcarriers. Not necessarily LTE. For LTE itself, we will discuss in the next session. Okay, exactly what types of subcarriers we have. In any case, we have one subcarrier called DC, direct current. It is right in the center of the spectrum, and it is not transmitted. There is no energy, no power at all. So if you are a UE who is looking for 700 megahertz, the carrier frequency at RF, so around 700 megahertz, wherever you find minimum energy, that is the center of your system, exactly 700 megahertz. That would be the carrier frequency. Then we have another type of subcarrier, guard subcarrier. Okay, and we just discussed that, right? So we have that guard on the left and right edge of the spectrum. Again, not transmitted. Okay, right and left side of the spectrum to minimize interference, right? To minimize interference to the adjacent system or spectrum. So we already know that. Another type of subcarrier is pilot. Who will answer this question? How do we use pilot in 3G system? Let's say 1X or DO or UMTS. How do we use pilot channel? What is the use of pilot channel in 3G? Okay, synchronization. Very good. That is one of the functions of pilot channel. So same idea here. We will use the help of pilot channel for synchronization. There are some other signals also. Okay, but the pilot, one of the functions is synchronization. Another function is it acts as a reference signal. So when we are trying to get our data, we will use pilot channel as a reference signal, and that will help us correct some errors on the data channel. So for example, let's say our pilot, let's say is 0000. And at that time, our data is, let's say, 0110. Now, sometimes the environment will mess up the pilot. So, this 0 will become 1. That is our error. And at the same time, our data bit will also be in error, because pilot and data will be affected in the same way. So, if you are a receiver and if you get 1 instead of 0, you know that that is a bit error. So if you want to get correct bit, you have to invert that bit. So you have to change 1 to 0. Same idea, if you get 0, then you know that that is an error. So if you want to get correct bit, you have to invert it. So change 0 to 1, and then you will be able to correct the bit error. That is the basic idea. This type of approach is called coherent demodulation. Coherent demodulation means that we use some sort of reference signal along with the traffic channel to figure out what bits were transmitted. So pilot acts as a reference signal to facilitate coherent demodulation. And also for handover measurements, we need to see whether we are getting good signal from a cell or not. If you are getting weak signal from one cell, a better pilot from another cell, then we know that, oh, we should do the handover so that we can get better quality from a new cell. So pilot channel is measured by the UE to facilitate handover or handoff. So those are some of the functions of pilot. Finally, the last type of subcarrier is data. This carries our user data. It carries also signaling. So your user traffic, email, web page, etc., along with the signaling message will be traveling on the data subcarrier. Okay, power control also. Power control, no, not on pilot. Okay, there is no. Power control also. Oh, okay. So even the power control bits are not sent on pilot, but yes, we use the help of pilot channel to do power control. So for example, in the uplink, the base station can send command to the user. The user will change the power of the pilot channel in the uplink, and then the data channel will follow the pilot in some fashion. That's how we use pilot in 3G systems. So that is correct. It helps power control. That is correct. Helps power control. In general. Here in OFDMA is a little bit different, but in 3G that will be correct. Okay, here in 4G we have a different way of operating. Okay, so we really I'm not doing power control, for example, in the downlink. Okay, Okay, there is still a question on pilot. Someone does not. Someone has questions on how pilot works. What is mapping of pilot? Okay. Okay. Let me try to give you another perspective. Okay, on pilot. Okay. Let's say F1 is a pilot subcarrier and F2 is data subcarrier. And the base station has given the UE 12 circuits, F1, F2, F12. There is one set. And out of that set, we said F1 is a pilot. Okay. And F2 is data. So now we are sending those subcarriers. Okay. So let's say F1, and let's call this time. F1 is 0, 0, 0. This is what is transmitted. Then F2 is data. Let's say we have some data bits 0, 1, 0. Okay. Again, this is transmitted. Okay. And now, what is received? So this was transmitted by E node B, and this is received by UE. Okay. So let's say pilot F1, we got 0, 1, 0. And we got data F2, we got 0, 0, 0. Okay. So this is what we received as a UE. Now we compare received pilot bits and expected pilot bits. We compare the two. So let's compare. Let's say this is what we receive. And what do we expect? We expect it always to be 0. So 0, 0. Okay, so there is a match. It means that there is no bit error at that time. It means that this data bit that we receive is okay because there is no bit error. Same way here, 0 and 0, perfect match. It means that data bit is okay, no error. But now let's look at this example, 0 and 1, now no match. This is an example where we have bit error on pilot. So we assume that there must be bit error on data as well because the pilot and data, they are close to each other, right? F1 and F2. So whatever happens to pilot, same thing must be happening to the data. That's what we assume. So must be bit error on data. So this, whatever we think that we receive, this is in error. So how do we correct the error? So we see, okay, this 0 became 1. Okay, so if you want to correct, we have to invert the bit. Okay, change bit from 1 to 0, 0 to 1. So we invert the bit from 1, because this is what we received, 1 to 0. That is for pilot. Same thing we will do for data. What did we get? We thought that we got 0. 0 is what is received. But now to correct, we need to change that, invert the bit, because we have to invert the pilot bit to get the pilot bit right. So to correct, we will invert the bit. Now this is exactly what the base station had intended for us. This was what was transmitted. So if we did not have a pilot channel, then we would have hard time figuring out that, oh, there was a bit error. But the existence of a pilot channel, the reference signal, helps us correct some errors. So hopefully this will give you the full-fledged answer. But if you have some additional questions on this topic, please stay with us after the session is over, and then we'll discuss it more. Okay? Okay, time for me to ask you a question. Please choose one of the options here. And of course, the way live meeting tools work, there is only one correct answer. And we are looking for something that is false. Okay, which of the three statements is false? Not true. Okay, which is false statement? And we have some questions that I'm answering right now.
Nisha, the poll is closed. I think.
Oh, what happened? Oh, sorry. Oh, now.
Here, I'll open. I just opened it.
Oh, okay. So I'm answering some questions, okay, while you guys are working on the. Okay. You guys are asking very, very good question. And I'm answering those, okay, so you can then okay, now think. Now again, false, okay, something is not right, okay. And when we say very little guard band, let's pick some number. Let's say 1 kilohertz. 1 kilohertz, okay. So when I say very little guard band, pick some number such as 1 kilohertz or 2 kilohertz, okay. So option 1. So think, what is an OFDM symbol? What did we define the OFDM symbol to be? For the second one, think what is the relationship between the symbol time and the subcarrier spacing. For option number 2, think what is the relationship between the modulation symbol time and the subcarrier spacing. And for the last option, think to maintain orthogonality in OFDM systems, do we need guard or we do not need guard. So think along those lines.
And
Do
just
we
a
need
reminder,
guard between two subcarriers to maintain orthogonality? In traditional multi-carrier, we had some sort of guard. Do we need that in OFDM or not?
and just a reminder to participants to check your questions and answers box in the lower right-hand corner, because Nishis has responded to some questions as well as, and so you can see those responses as well as the questions.
And you can provide the answer by selecting the button, the radial button on the left side of the choice. Okay, you do not need to type. If you do, you can just simply click on that circle that is on the left side of the statement. Because sometimes some folks are giving me the answers through questions and answers. That is fine, but to make your life easy, you can just click on the left side of the choice. Okay. So let's close the poll and let me show you the result. Okay. Now, first thing I would like to say, okay, that today and in future, when you see these kinds of options, then pick the best possible answer. Okay, the best possible answer. Okay. So let's go one by one. The first one says OFDM symbol is a combination of modulation symbols on multiple subcarriers. That is a correct statement. That is the definition. What is the definition? An OFDM symbol is nothing but all modulation symbols on all subcarriers, because one subcarrier carries one modulation symbol, another subcarrier another modulation symbol. So that is the definition. So we should not choose that as our answer, okay, because we are looking for a false statement, not the true statement. And sorry about that, but that's the way this Microsoft Live meeting allows us. We can have a single correct choice. Okay. Yeah. Anyway, the second one, okay, that will require very simple mathematics. Okay, we are saying faster symbol rate. Okay. So faster symbol rate means many symbols every second. If you have many symbols every second, what happens to the symbol time? The symbol time goes down, right? So when you say that you have faster symbol rate, then you have many symbols per time. So symbol time goes down. Okay, if you have very fast symbol rate, it means that symbol rate is going down. Now we mention the relationship between the subcarrier spacing and the symbol time. Inverse relationship. So if your symbol time goes down, if the denominator goes down, what happens to the ratio? The ratio goes up. It means the subcarrier spacing goes up. It means the faster the symbol rate, lower the symbol time, and it means higher the subcarrier spacing. And currently, our poll, the second choice, says that the faster the symbol rate, greater the spacing, the larger the spacing. So that is a correct statement. It is true. And since it is true, we cannot choose that as the answer, because we are looking for a false statement, not a true statement. Let's look at the final choice. About 50% of you chose that. But I was just playing with the English language, sorry about that. But remember, there is absolutely no guard band required between two adjacent subcarriers. That is the power of OFDM. A traditional multi-carrier system indeed requires guard band because you want to minimize interference between two adjacent subcarriers. But in an OFDM system, to maintain orthogonality, there is no guard band at all. The way to construct orthogonal subcarriers, I already mentioned. 1 cycle of sine wave, 2 cycles of sine wave, 3 full cycles of a sine wave. That is the way of constructing orthogonal subcarriers. There is absolutely no guard band required between two adjacent subcarriers. So when I say where is the guard band, and I told you that let's say 1 kilohertz is an example. Okay, so absolutely zero guard band required. Okay? Because the way the definition says, if the definition is, what is the definition of guard band? Right? That is some space wasted, and we are not wasting any space. Okay, so that's what we have for this OFDM poll, and let's see. Okay, so time for a short break. So we will give you a 10-minute break. Okay, just like yesterday. So the break starts now. Okay, so you can rush to your coffee room, restroom, whatever you want to do. You have 10 minutes. Okay.